Hello everyone. First of all, let me say thank you for stopping by and watching our presentation. My name is Braulio Matias. I am the team lead and I was one of the primary contributors for the simulation analysis, formatting of the reports submitted, as well as the gathering of data of testing results of the prototype.
I'm Kelly Muller, and I was in charge of creating test plans, editing and submitting documents, as well as preparing the video presentation.
Hello, my name is Jonathan Sepulveda. My primary contributions were being the team's procurement representative as well as budgeting.
Hi, I'm Arianna Rodriquez, and I was in charge of the material selection, the optical system, and the 3D printing.
Hi, my name is Jared Black. My main contributions to the project were computer-aided design, editing of documents, and material selection.
Hello, my name is Evan Gonzalez. My primary contributions to the team were theoretical calculations, CAD modeling, and manufacturing operations.
Besides everyone's individual contribution, everyone also contributed equally in the concept generation design and project documentation.
The average American family uses more than 1,135 liters or 300 gallons of water per day at home. To many families in America, having access to fresh water is something they don't struggle with. However, this is not the case in many places of the world, especially in third world countries. Approximately 790 million people don't have access to a source of fresh water. This can be due to low income, local terrain, and many other reasons. That's 11% of the world's population going day to day without meeting the daily recommended intake of 2 liters or half a gallon of water per day. Our goal is to provide a solar desalination unit that will turn local brackish and salt water into drinkable fresh water for families that do not meet these needs. The end product goal is to provide 11 to 19 liters or 3 to 5 gallons of drinkable water per day while remaining a price affordable for those with low income in third world countries.
The motivation behind choosing solar desalination was the ability to aid those in need, like in underdeveloped areas. Water is a basic human necessity, and we wanted to find a way to supply this to those who may not have the technology to do so. Our solar desalination project allows us to turn the salt water into drinkable water without the need for electricity. Thus, this is targeted towards third world countries and underdeveloped areas that have access to salt water but not fresh water. However, this is also applicable to natural disaster zones that leave many with no electricity or running water.
After considering many options of solar desalination systems to build, we ultimately decided on a step-based system. By splitting the system into multiple water basins, heat can be absorbed by the water more effectively as there is a greater amount of surface area for the water to be spread out onto. Emphasis was placed on the dimensions of the boiler, more specifically the dimensions of the step assembly, around which the rest of the desalination unit was to be designed. Each step is 24 inches long, 4 inches deep, and 4 inches tall, with a total of 6 steps. Of course, in order to retain a thin film of water on each step, there is some overlap on the vertical section, which is 5 millimeters. These are the critical dimensions of the step assembly, and from there, the remaining geometry was created. Solar energy is captured by the system, and using reflectors on the backside of each step, as well as the reflectors mounted on the sides of the desalination device, is amplified and used to evaporate the salt water in each basin. The water vapor condenses on the condensation surface, which takes the shape of a triangular prism or a rooftop made from acrylic in order to maximize the area for the water to condense on. This configuration completely covers the boiler and is sealed around the edges so that no water vapor is lost, which would hurt the efficiency of the system. Gutters mounted on the sides of the condensation surface collect the fresh water as it drips down the acrylic and channels it to a half-pipe configuration located just above the bottom step. At an angle of about 5 degrees, this half-pipe collects the fresh water from the gutters mounted to the condensation surface and channels it out to the fresh water container.
In order to have a better understanding of the system behaviors, the team decided to run a simulation analysis, as well as to acquire knowledge on a simulation software. The simulation software selected was ANSYS Fluent, as it is recognized to be one of the best softwares for CFD simulation, and it also offers a solar ray tracing feature, which allows for more accurate results. 2 videos will be shown, in which the first video at the top is a contrast between the water volume fraction and the temperature of the system, and the second video is a contrast of a water volume fraction and the steam volume fraction of the system. By looking at the second video, it can be seen that the simulation software does a fairly good job at showing the steam distribution along the system. However, if close attention is paid to the temperature contour in the first video, it can be seen that the temperatures drop to the negative values at some point. This is not possible given that the ambient temperature was set to be 26 degrees Celsius. With the help of a faculty member, it was determined that this simulation was not a good representation of our system. However, significant knowledge on the ANSYS simulation software, as well as the importance of a good mesh, were acquired through this process.
The next stage of the project was the assembly process. Due to the limitations of COVID-19, we wanted to minimize in-person contact. This was resolved by extensive planning before the assembly days to ensure efficiency. In all in-person activities, CDC guidelines were followed, such as wearing masks and staying distanced wherever possible. Motivation to continue the project despite the challenges of COVID-19 was maintained due to the broader impacts this project can have. A technical challenge that was faced was keeping the steps aligned properly at 90 degrees. Initially, the steps were glued together and held in place with clamps and weights, which resulted in an unlevel structure that did not fit into the system. This was redone using screws to hold the pieces together, which provided a more accurate alignment. Advice was taken from the faculty advisor for multiple components. Examples where advice was taken include considering multiple depths for the water level in the steps, choosing an IV administration set as the inlet, and making sure that the reflectors were easily removable. Once the finishing touches were completed, the system was finished and ready for testing.
Hi, this is our system demonstration. Right here we have our inlet jug that contains all of our salt water. That's then siphoned through this tube, connecting to an IV administration set. This administration set helps us regulate the flow rate into the system. About every 30 minutes we come out here and test the temperature of the water with this thermometer, and about every 4 to 5 hours we come out here and move the entire system facing towards the sun. As the system heats up, it condensates on this surface, and through our gutter system it routes all the water on the edge of the system through until this tube exports it to the outlet jug containing fresh, clean water.
Continuing on with the system demonstration, this is a time lapse to show a sped up version of running a test. You'll see us come out to take temperature measurements and tap on the acrylic to make the droplet process go faster. You can begin to see the droplets as they form and fall down the condensation surface. The span of this video is about an hour and a half worth of time. It also contains a turn of the device.
In order to have sufficient data from the prototype, the system was turned to face the sun as needed, the ambient system temperatures were recorded, and the volume of fresh water produced and its salinity level were recorded. Right next, we have two plots of the first day of testing, in which the first plot is a temperature versus time, and the second plot is a volume versus time. It can be seen how the highest temperatures were reached between 10:30 a.m. and 3:30 p.m., in which they were averaging about 60 degrees Celsius. Within these times, we also had the highest production rates, and at the end of the day, we end up with about 1.8 liters of water. Even though this did not meet the project's goal, the salinity level recorded for the freshwater produced was between 0 and 0.5 parts per thousand, which is the recommended salinity level for drinkable water. One of the biggest lessons learned from this process was the importance of team communication and trust, as lack of communication within a team can be detrimental towards the team functionality, and one should be able to trust their peers in case one doesn't have enough knowledge in a subject, such that another peer will be approached and that peer might have enough knowledge on the subject to help you learn and succeed on meeting deadlines. Once again, we want to thank you so much for watching our presentation.